Welcome to this explainer. Look, if your application runs beautifully in staging, but then completely catches fire the second it hits production, well, you are exactly in the right place. Today, we're stripping away all that clean textbook theory to reveal what senior engineers actually know about scaling massive backend workloads. We're going to bridge the gap between classroom ideals and the blood pressure-raising realities of managing high-throughput systems. So, let's get right into it. Okay, let's dive right into a scenario that has definitely caused a few sleepless nights. Picture this. You run a completely safe database migration. You didn't drop any columns. Everything looks absolutely perfect. But then a nasty bug surfaces, and you have to roll back your application to version 1.0. Suddenly, the rollback fails entirely with a serialization error, and your production database just grinds to an absolute halt. You didn't touch the schema during the rollback, so why on earth did it break? The answer is something called data poisoning. It sounds dramatic, right? But the reality of production is that while your version 2.0 was live, it started saving new JSON data shapes into your database. Even though the schema itself didn't change, the data's shape did. So version 1.0 has absolutely no idea how to parse that new JSON. Senior engineers know a fundamental truth here. Rollbacks are only for code. They are never for data. To fix this, you don't roll back the database, you actually have to roll forward by deploying a version 1.1 that includes a compatibility parser for that newly shaped data. And that is just one example of the harsh realities of scale. Here is our roadmap for today's explainer. We're going to cover hidden database nightmares, distributed system trade-offs, the observability trap, why systems actually fail, and we'll wrap up with my favorite topic, delete more code. All right, section 1. Hidden database nightmares, specifically the N+1 dilemma and indexing traps. Let's look at how junior assumptions about database interactions completely fall apart at scale, especially when you're dealing with high-throughput transactional systems. Let's stick with migrations for a second. If you try to run a standard alter table command on a table with, say, 500 million rows, you're going to lock that table for hours. Your application will be literally dead in the water. This is exactly why seniors rely on online schema change tools like Ghost. These tools are brilliant because they execute 3 steps totally invisibly. First, they create a ghost table. Then they copy the data over in small chunks in the background so they don't overwhelm the main database. And finally, they perform a lightning-fast atomic swap to replace the old table. Boom, 0 downtime. Now, beyond migrations, your query structure is another massive trap. Take the infamous N+1 problem. Imagine you're fetching 100 users, and then you make 100 individual queries to fetch the related data. That's 101 queries, taking maybe 800 milliseconds. By replacing those 101 separate queries with a single eager loading batch query using a join, you can complete the exact same task in about 15 milliseconds. That is a staggering 54 times performance improvement, instantly dropping your cloud compute costs and slashing your latency. Of course, even a perfectly eager loaded query is pretty much useless without proper indexing. The fundamental difference between a full table scan, which operates at O of n complexity, and traversing a B-tree index at O of log n complexity is night and day. Think about it. For a table with 1 million rows, a full scan requires 1 million operations. An indexed lookup, about 20 operations. This basic mathematical reality explains why proper indexing yields 100 to 1,000 times performance improvements in your database. It's a total game changer. But here's the trap. Developers learn about indexes and then just index everything. Over-indexing actually slows down your insert and update operations, basically killing your write performance, and it totally confuses the query optimizer. So the crucial takeaway here is avoiding these common mistakes. Always put equality conditions before range conditions in your composite indexes. Never index a low cardinality column like a Boolean flag. The database will just ignore it, and you're just wasting storage space. Limit your indexes to about 5 to 7 per table, and never, ever assume an index is working without actually verifying it using the explain command. Moving on to section 2, distributed system trade-offs and surviving the network partition. Zooming out from the database level, we hit the chaotic, messy world of distributed systems. At a massive scale, your components are separated by networks, and network partitions are an inevitable reality. They are not just a theoretical possibility. Wires get cut, routers fail, you simply have to design for it. Which brings us right to the CAP theorem. This dictates that during a network partition, you have to choose how your system behaves. You literally cannot have it all. CP systems choose consistency. They protect correctness, think of financial data, by rejecting or delaying requests during a partition. AP systems, on the other hand, choose availability. They keep an e-commerce catalog highly responsive by accepting writes on isolated nodes, even if it means temporary inconsistencies. As an engineer, you have to know exactly which trade-off your business actually requires. But CAP only talks about what happens during a failure. Going a step beyond CAP, we have the Passel-C theorem, which forces us to realize that even when the network is perfectly healthy, you still have to make a choice. You constantly trade stronger consistency for lower latency. If you want a read to be instantly fast across the globe, you might just have to accept that the data you're serving is slightly stale. And to manage that latency, we use caching. But notice how senior engineers apply very specific caching patterns based on those exact trade-offs we just talked about. Cache aside is generally your best default. Write through prioritizes consistency, but it will slow down your writes. Write behind gives you blazing fast performance, but, and this is a big but, you have to be completely okay with potential data loss if the cache crashes before writing to the main database. Massive companies like Amazon utilize these exact in-memory caching strategies to cut long-tail latency across their microservices. All right, section 3, the observability trap. This is what happens when your monitoring costs more than your actual compute. Moving up the stack, we arrive at operations and observability. Junior developers often think logging absolutely everything is the ultimate best practice, until, of course, their CTO actually sees the cloud bill. Here's the deal. If you instrument every microservice with thousands of custom labels, like user IDs or session tokens, you trigger what's known as a cardinality explosion. Every single unique combination multiplies the memory usage of your metrics database. At scale, your monitoring costs will actually exceed your application's compute costs. It's crazy. Seniors know you have to be highly strategic. You only instrument the most critical business pivot points, rather than tracking every individual user's granular movements in your expensive metrics. To manage this efficiently and, frankly, economically, the industry has shifted heavily toward open telemetry. By utilizing an open telemetry collector, you invest once in instrumenting your services. It acts as a proxy, seamlessly receiving and batching your telemetry data. This means you keep your application code completely untouched, even if you decide to switch observability vendors down the line, completely destroying the massive vendor lock-in that used to really plague this industry. Section 4. Why systems actually fail and the myth of hardware failure. So, okay, you've optimized your database, you've balanced your CAP trade-offs, and you've managed your logging costs. You feel pretty invincible. But why is production still crashing? Well, it's really not what you think. People love to blame commodity hardware or their cloud providers, but when you look at the actual data from large-scale internet services, operator configuration error, meaning human node operators, accounts for a massive 33 to 45% of failures. Human error, not hardware failure, not network outages, is actually the leading contributor to user-visible failures in massive distributed systems. It's the wrong configuration file. It's the bad deployment. It's the accidental deletion. And ironically, when engineers try to protect against these failures, they often shoot themselves in the foot with costs. For example, running daily automated restores to verify your 10-terabyte database backups seems like a really smart idea until the massive cloud egress and storage costs hit your desk. Seniors adopt much smarter strategies. Instead of full daily restores, they perform a sampling restore on critical tables only. Or they'll run full drills just once a week while relying on daily metadata checksums. It's all about protecting the system without bankrupting the company. Finally, we reach Section 5, delete more code. The ultimate senior mindset. We are at the most counterintuitive architectural advice you will ever receive. Everything we've talked about so far today is about managing complexity, but the absolute best way to manage complexity is to eradicate it completely. I absolutely love this quote. Senior developers don't write better code, they delete more of it. Because every single line of code is a liability. It adds cognitive load, it requires constant maintenance, and it's a potential hiding place for bugs. The developer who gets promoted isn't the one shipping the most complex, sprawling features, but the one who is systematically eliminating complexity from the system. Picture the typical career progression of a backend engineer. A junior developer joins the team and adds 50,000 lines of code in their first year. They're building elaborate failover systems and all these just-in-case abstractions. Their GitHub contributions look like massive mountain peaks. A senior developer joins that exact same team and, in month 1, deletes 15,000 lines. They remove unused microservices, they consolidate redundant functions, and they eliminate premature optimizations. They realize that the absolute best code is no code at all. Which brings us to the end of our explainer. I promise you, your future self, your teammates, and your users will all thank you for the simplicity. So I'll leave you with this final, somewhat provocative thought for your next sprint. Next time you sit down to architect a brand new feature, before you write a single line of code, ask yourself, what can I delete instead? Thanks for joining me on this explainer, and I will catch you in the next one.